everybody, this is Dr. Nigro with a Physics Fundamentals Screencast. This is the first in our unit that looks at momentum and collisions. This particular screencast is going to focus on momentum and impulse, and then how impulse can change the momentum of an object. All right, so we're going to start with momentum. All right, a momentum is defined as a measure of mass in motion. All right, and really we can think of it in terms of inertia in motion. So objects that have a lot of momentum, it can be difficult to change their motion, whereas objects with low momentum, it can be a little bit easier to change their momentum. So the way I tend to think about it is, if you were going to be in a car accident and you had a choice of driving a semi-truck or a tiny smart car, most people are going to pick the semi-truck because they feel that the mass that that object has, it's not going to be as damaged because it has a lot of momentum. All right, whereas the smart car with its low mass tends to be the object that gets pushed around in an accident. So when we talk about mass in motion, we're really talking about its resistance to change in its motion. All right, so momentum is represented with a lowercase p, and we calculate it by multiplying the mass of the object times its velocity. So the unit is going to be a compound unit of kilograms times meters per second. So we need to make sure that our mass values are in kilograms and that our speeds tend to be in meters per second. You could also do momentum in other speed units like kilograms times kilometers per hour. It just needs to be a unit of velocity versus mass. All right, now objects that have high momentum, that can come in two different forms. We can have high mass. All right, so that would be our semi-truck. All right, it would come down the highway. It would have a lot of momentum because it's going to have a lot of mass behind it. Or we can have an object that has high velocity. All right, so an object that could be really small, such as an atom, but move very, 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 very fast. And so because of that, it also would have a high degree of momentum. And of course, we can have objects that have both. They have high mass and high velocity, so they will obviously have a very high momentum value. All right, now momentum, as it's got velocity in there, is a vector quantity. All right, so you need to watch your signs. All right, in other words, watch your direction. All right, so if an object is moving forward, to the right, or up, we've designated those as positive directions, so they would have positive momentums. If the object is moving backwards, to the left, or down, those are our negative directions, so we would have negative signs there. So don't be surprised if you're working problems and you have negative signs pop up. That just tells us the direction of that particular velocity value. All right, now we can calculate the momentum of a particular point in an object's journey, which can be interesting, just give us an insight into the mass and velocity of that object. But more interesting to us is going to be when forces or other objects interact with our object, how does that momentum change? All right, so the change in momentum usually comes about because of a change in the object's velocity. We don't create or destroy matter, and so while an object's in motion, we don't tend to lose or gain matter. So the mass value tends to stay the same, but the velocity value can change. All right, so we know from our other screencasts and other formulas that delta represents change. The change in momentum is going to be equal to mass times the change in velocity. And to calculate that change, we're going to need to know the final velocity, and then we'll subtract out the initial. We also could know the final momentum and subtract the initial. That's another way to determine that change in momentum. So it kind of depends on what the problem gives you. Now, when we have these situations here, all right, these tend to be caused by interaction with an outside unbalanced force, which makes sense because we have a change in velocity. That means acceleration is happening, and we know that acceleration, according to Newton's second law, means there's a net force that's acting on that object. All right, so the change in momentum tends to be caused because of an unbalanced outside force. All right, so let's talk a little bit about those forces. So for example, let's just say we have two carts and we're going to let them run into each other. All right, so we have cart A, and it's moving to the right, and then somewhere out in front of it is cart B, and we'll make it move to the left. All right, so when that collision happens, cart A hits cart B, and we know that cart B hits cart A. All right, well, if we remember from Newton's third law, for every action there is an equal and opposite reaction. The force that is exerted by A on B must be equal and opposite to the force exerted by B on A. And these forces can cause a change in the velocity of the two objects. And if we have a change in velocity, we're going to get a change in the momentum. All right, so these forces that occur during these collisions, these impact forces, those are what are causing the change in the momentum of our objects. Now, these forces, because they occur over such a short time period, have a special name, and we call them impulse interactions. All right, so impulse is represented by a letter J. All right, this is a force that causes a change in the momentum of an object, and it takes place, should be over a short time. All right, so to calculate the impulse that is causing this change in momentum, we need to know the value of the force, and we need the time over which it is applied. All right, and so our unit for impulse is going to be a Newton times a second. All right, so here's our third formula. All right, now, as I said, this causes a change in that momentum. So what that really means is that the impulse is equal to that change in momentum. All right, so again, this causes the change in momentum. All right, it's not the other way around. We don't have a change in momentum that causes an impulse. It's the other way. The impulse occurs, it's causing this change in our momentum. And that leads us to a theorem called the Impulse-Momentum Theorem. And we're going to talk about this a little bit when we work one of these problems. And what that tells us is that the impulse causes the change in momentum, so the force times the time of the impulse must be equal to the mass times the change in the velocity of our object. All right, so we can mix and match, basically, the impulse and change of momentum formulas. Let's say I know the force and the time, but I'm asked for the change of momentum. Well, I just calculated force times time, and that is the impulse, which in turn equals the change of momentum. Or maybe I want to figure out what the impulse was, but what I know is the mass and the velocity values. Well, I can use those, calculate the change of momentum, and that equals the impulse. So it's just a matter of swapping out our units. All right, so we're going to try a couple of these. These are pretty straightforward problems, and then we're going to end by talking a little bit more about the relationships between some of these variables. All right, so here, which is going faster, a 1,200 kilogram car with a momentum of 30,000 kilograms times meters per second, or a 1,750 kilogram car with a momentum of 35,000. All right, so for these problems, we've got a mass and a momentum, and we're asked to find velocity. So we know that momentum equals mass times velocity, and if we rearrange that, velocity equals momentum divided by the mass. All right, so for cart A, which I'm going to call this guy, all right, we're going to have 30,000 kilograms times meters per second divided by the mass of 1,200 kilograms. All right, so our velocity of this object must be 25 meters per second. All right, we're going to repeat, but with B. So momentum equals mass times velocity, which means velocity is momentum divided by mass. All right, so this time we have a momentum of 35,000 kilograms times meters per second. All right, we're going to divide that by the mass of 1,750. So we're going to have a velocity value here of 20 meters per second. All right, so here's our first relationship. So you can see that even though the momentum value of cart B was higher, All right, the speed at which it's going is lower, and that's because of the relationship between mass and velocity. All right, if we look at our momentum equals mass times velocity formula, right, these two are on the same side of the equal sign, so they are inversely related. All right, as the mass value goes up, we'll see a decrease in the velocity value. All right, now it's not vice versa. We can't use speed to make matter. All right, but if the velocity value changes, that will impact our velocity value. All right, let's try another one. A 2 kilogram ball is moving with a velocity of 15 meters per second when someone catches it. What is the change in momentum? All right, so I've got a mass, I've got an initial velocity, hopefully a final, and I'm looking for change in momentum. All right, so mass of 2 kilograms, an initial velocity of 15 meters per second. And if someone catches it, I'm going to assume that that final velocity must be 0. So what is my change in momentum? All right, so change in momentum is mass times change in velocity, which is v final minus v initial. And I'm just going to plug everything in. 2 kilograms, 0 minus 15 meters per second. And I'm going to get a negative 30 kilograms times meters per second. All right, so the momentum value is negative here. All right, and in this case, that tells us that the object is slowing down. All right. All right, let's try another one. How much force is needed to exert an impulse of 50 newtons times seconds for 15 seconds? How about 2 seconds? How about 0.003 seconds? All right, so we've got a mass value. We've got a, oh, I'm sorry, not a mass value. Oops, wrong problem. We've got an impulse value. We've got a time, and we're asked to find the force. All right, so the impulse is 50 newton times seconds. And we've got a time of 15 seconds, 2 seconds, and then 0.003 seconds. And we're going to need to find the force value for each one of those. All right, so we use our impulse formula. Impulse equals force times time. But because we're looking for force, we're going to rearrange it. So the force equals the impulse divided by the time. All right, so we'll start with our first time. So we've got 50 newtons times seconds divided by 15 seconds. So we have a force that occurred that was around 3.3 newtons. So there's our first force. All right, now we're going to repeat, but for 2 seconds. So force is equal to impulse divided by time. So 50 newton seconds again, but this time divided by 2 seconds. All right, so our time has decreased. And when we do our division, we find that our force has gone up. So there's another relationship, force and time. All right, let's do it one more time. Impulse divided by time, so 50 newtons times seconds divided by 0.003 seconds. I would expect to see a big jump this time because that has a very small amount of time. 16,667 newtons, yes. All right, so you can see, if we look at this formula, all right, force and time are also inversely related. All right, as the time over which the force is applied goes down, then the force that was felt in that impulse is going to go up. If the time goes up, then the force that is felt is going to go down. All right, and this is going to be really important. We're going to talk about this again in just a few seconds. All right, so here's a problem that's got a little bit of everything. A 1,200 kilogram car travels at 30 meters per second when it hits the brakes. The braking force of 2,000 newtons lasts for 7 seconds. What is the car's final velocity? All right, so we have a mass, some velocity values, a force, and a time. So mass of 1,200 kilograms, our initial velocity is 30 meters per second. We're asked to find our final velocity, a braking force. So they're braking. That means that we're applying a force that works against the motion. So it's negative 2,000 newtons, and that force is applied for 7 seconds. All right, so we know that force times time equals mass times v final minus v initial. So here's our formula. Let's plug in what we know. Negative 2,000 newtons times 7 seconds is going to be equal to the mass of our car, 1,200, and we're going to have our unknown minus 30 meters per second. All right, so we start doing some multiplications. We get 14,000 newtons, 1,200 kilograms, and v minus 30 meters per second. So I'm going to divide both sides by 1200 to move it to the other side. All right, and that's going to leave me with a negative 11.67 meters per second. And that's going to be equal to v minus 30 meters per second. I add that 30 meters per second to both sides, and I end up with a final velocity of 18.3 meters per second. All right, and I ask myself, is that reasonable? It is. It's less than my initial velocity, which I would expect if I am braking. All right, if you do not do your signs correctly, let's say you flip your velocity values, like you put it v initial minus v final, or you don't put a negative 2000 in for that braking force, you are going to get a velocity value that is greater than your initial, and that should not be the case if we are braking. So make sure you're reading the problem and that your answer makes sense. Okay, so this last problem is going to look at that relationship again between the force and the time of an impulse. All right, so let's say you're traveling in an out-of-control car. All right, would you rather run into a snow pile or a concrete wall, and why? All right, so I asked my students this question in class, and I got a lot of different answers. One person said it seems softer to run into the snow. All right, and that seems reasonable to me. Oh, and I should preface this by saying everybody said run into the snow pile. Nobody wanted to run into the wall. Someone else said snow will cushion the impact, which also is a good answer. All right, because that is what snow is going to do, right? It's going to kind of slow you down. And that was really, eventually we got around to that it's going to takes longer to come to rest in the snowbank versus hitting the wall. All right, if you hit a concrete wall, that collision takes no time at all. It's over. All right, whereas if you're trying to plow through something and it's cushiony, softer, slows you down, all right, then the time over which the force is applied is going to drop. All right, so when we think about a collision, I'm going to come down here for a second. Oops. All right, we know that our car has a mass and we've got velocity values, right? Well, it doesn't matter what you do in that collision. The mass is going to stay the same, and this change in velocity is going to stay the same. So the only thing that I can influence during a collision is the force and the time, all right? And the easiest of those two is going to be the time. So when you talk about collisions and safety features, you're really talking about how can I affect the time over which this collision occurs. All right, so we've got two examples here. The first one, you're going to be driving your car 25 meters per second in AB's parking lot. You make a really wrong turn and slam into the side of the building. If the time of impact was 0.2 seconds, what was the force of the impact? So we're going to have mass, velocity values, force, and time for this problem. So our car is 1,000 kilograms. We have an initial velocity of 25 meters per second, and our final velocity will be 0 because we're going to come to rest. We're asked to find the force, and we know the time was 0.2 seconds for that impact. All right, so force times time is equal to mass times the change in velocity, so v final minus v initial. Force times 0.2 seconds is going to be equal to 1,000 kilograms times 0 minus 25 meters per second. All right, so we say force times 0.2 seconds is going to be equal to negative 25,000 kilograms times meters per second. And then we're going to divide both sides by 0.2. So the force is going to be negative 125,000 newtons. So that's a lot. That's a lot of force. All right, that's going to leave a mark on your car and potentially you. All right, so we're going to repeat this calculation. All right, you're driving your car, still 1,000, still starting at 25 meters per second in the parking lot. But this time we realize we're about to run into the building and yank the wheel so that we run into a pile of snow instead. All right, so the time of impact is now 2 seconds. So what was the force of the impact? So again, mass, initial and final velocities, force, and time. So our mass value is the same as part B, or part A rather. Our initial velocity and our final velocities are the same. So the change of velocity is going to be the same. All right, what we have adjusted is our time. So instead of 0.2 seconds, now it's 2 seconds. All right, so same formula, force times time equals mass times final velocity minus initial. We plug in our time of 2 seconds, our mass of 1,000 kilograms, and then our two velocity values, 0 for final, 25 meters per second for initial. All right, repeat our calculation. We're going to get negative 25,000 kilograms times meters per second for that change of momentum divided by our 2 seconds. And this time we have negative 12,500 newtons, which is 100 times less than what we saw for part A above. All right, so if you look at these two problems, the mass was constant, all right, and the change in velocity was constant, which is what will happen in a collision. All right, what we could change was time. So the time increased, and what we saw was a decrease in the force. All right, and that's important. I mean, if you can stretch out the time of a collision, then you are going to change the force that will impact the change in motion of that object. All right, so we have lots of safety features that help with this. I mean, that's the whole point of an airbag in your car. All right, instead of you slamming into the dashboard, the airbag, it provides a cushion, and you still move forward into that cushion, but it increases the time of that impact. All right, same thing with seat belts. All right, same job. All right, its job is to slow you down, all right, so that the time over which your body feels that impact goes up. Okay. All right, so this is our look at momentum and impulse and how impulse can change the momentum of an object. You should understand the formulas, and in particular, you should appreciate the impulse-momentum theorem and the relationships that we can find within that formula. Okay?